going to start with this new study theme called the frequency response or frequency domain analysis. And I want you to understand that there's two separate routes by which we can arrive at something that resembles frequency response analysis. The textbook begins, and I'll begin today, with a physical interpretation that is based on applying a sinusoidal input to a system. But I find that a lot of students find that a little bit abstract, or let's say there's kind of a question, which is, how can it be that we can learn something from applying a sinusoidal input to a system, since we so infrequently apply sinusoidal inputs to any of the systems that we interact with in our day-to-day lives? But let me just kind of tell you this basic thing that I'm going to, you're going to have to just take this effectively on faith. I mean, you can do the math, it does work out, but the fundamental idea of frequency response analysis is that if I take a linear system, and I'll particularly here, in other words, I've got a G that is described by linear differential equations or has a corresponding transfer function. Those are equivalent statements, right? So if I have a transfer function, polynomial over polynomial, or a rational transfer function, I have a linear system. And linear systems have this interesting property that if I apply a sinusoidal input, right? So that's the sinusoidal input. And I keep doing that, quote unquote, forever. The system output will also move in a pure sinusoid as well. Now, this is a property of linear systems only. In fact, if the system is nonlinear, reliably, like we can kind of almost express the extent of nonlinearity by how far that response deviates from a sinusoid. And if you're thinking like, let's say, like how would this work? Remember, if we're saying something like, I've got my tank, what this means is if I take a varying input, so picture your bath or whatever, and you're just moving open and close the tap, right? You can understand that in the times when the flow is high, the level will start rising. But now just notice the language that I'm using here. We don't expect for these sinusoids to match up 100% in time. So I'm just, let's choose a different color here. So if I draw the input and the output on the same axis, let's say that's 0, and I've applied a sinusoid of this nature. This is the input. If I'm talking about the level, what I expect is that when the system is high, or when the input is high, let's see what's a nice color. Let's say here. So at this point here, when the input is at its highest, the rate of change of the level is at its highest. Okay, in other words, the level will be going up. It won't be itself as high as it will ever be, right? Because it'll keep going up. And so let's say the level starts here, because we can see the sinusoid starts at 0 or at some steady state, right? And then goes up from the steady state. And this is an important point also to remember, that these curves, we're not talking about sinusoids that were sinusoidal forever. We're talking about these special sinusoids that start at 0 and then become a sinusoid. Why do we say that? Because all of our signals are like that. Right? Every single signal that we've ever analyzed in this module, using Laplace domain techniques, we've arranged for it to be the case that all things were 0 when they started in deviation variables. So the level, and I'm drawing them separately here just so that you can kind of distinguish them. And they'll have different units of measure and so on. So like just walk with me a little bit on this. But think about what will happen. The level was constant, right? So this is the level. It was constant, and then I started increasing the flow rate. And when you increase the flow rate into the tank, the level will start to rise in response. But it will rise when the flow rate is still very close to zero, it will rise very slowly. And so we expect kind of this shape. Does that make sense? So that kind of higher order, it's not a sharp response, it's like it's starting to go, right? If you want to explain this to yourself, this is almost like that first little bit of a sinusoidal input is like a ramp input, right? So it's like a little mini ramp in that first little bit. You guys remember that sine of x is very close to x for small x. Okay. And now at this point over here where the flow is the maximum, that's the inflection point. That's the fastest rate that the tank will ever take to change. And as soon as that flow rate starts going down, the rate at which the level changes will also start going down, which means it'll start making it'll like the curve the other way, right? And then we run that argument the same way, but then like in reverse, because as soon as the sinusoid now dips below the steady state, the level will start going, well, actually, technically, at some point, a little bit before that, the level will start going down, right? But anyway, when the flow rate is low, the level goes down. When the flow rate is high, the level goes up. And that effect leads to this kind of response. If we just kind of follow the same, now I've obviously sketched that freehand, so don't like call me on, it's not exactly a sinusoid. So I can also not draw a perfect circle. But that's roughly what we expect. And I want you to understand the process by which I've done this, right? Like I've done this using my mind, like I expected you to do in semester test 2. Very useful, right? To picture this. And we can see that if we keep doing this, we eventually see this kind of sinusoidal behavior emerging. Now, it turns out that if you actually do the math, you find that there are these two separate regions. And I mean, I'm going to say separate regions, but, you know, actually, what happens is the level is some function of time, and what we'll see is that that function is an exponential term and a sinusoidal term. And the exponential term has this property that it goes to 0. And the sinusoidal term then remains. And so what we see is that there's this area here that is called the transient. And I'll show you the actual, I want to sketch it just so that you get a feeling for it. But I've got a nice GeoGebra notebook that I'll switch to now that shows this effect immediately. And we say that there's this transient response because the transient response is effectively like the system going from steady state and kind of being struck by this new sinusoidal response. And in other words, there's kind of a short time during which the response is kind of just getting going. And we call that a transient response. And then there is the eventual response. And as we go on in time, only this sinusoidal term remains, because that exponential term completely falls away. And we can kind of figure out by looking at the math what the properties of that sinusoid will be, which I'll also introduce you to. But this is like the first important understanding that you need to understand. Part of this is nomenclature, and part of this is just like you understanding that this is a thing that we can do. We can apply a sinusoidal input, we can observe the output, and for linear systems, eventually the output resembles a pure sinusoid itself. And it is important to understand that we're talking about the eventual behavior. Whenever we're doing frequency domain analysis, we are assuming that the transient stuff is past. So when we pronounce any things about the system based on its frequency response, we're effectively saying this is what the long-term sinusoidal behavior looks like, not what the transient looks like. To do the transient, you actually just had to solve the equations. But we learn a great deal from doing frequency domain analysis, partly because of the fact that Fourier series are a thing. And I'm going to take you a little bit through that, because I want to link into your mathematical intuition in addition to your physical intuition, to link the Laplace domain and the frequency domain strongly in your minds. We have a first order system. This is now exactly just the first order, but the concepts work very much for any kind of order of system. And you can see here the calculations that I was talking about earlier, where this is the actual math. If you were to use SymPy to do the Laplace transform and inverse Laplace transform of a sinusoidal input and the resulting output, you would see this idea. So here, this blue line is the input sinusoid. The red line is the true analytic result of that input sinusoid. Take note that all of those two signals have been 0 for times less than 0. And the orange line is the sinusoidal approximation or the eventual behavior. And now you can see what I mean, right? You can see that the initial response, and especially if you kind of zoom in there, you can see how closely that resembles just like a ramp response. So there's like a first order ramp response. So it kind of gets going and then it settles into the sinusoid. And from around here, the pure sinusoid approximation and the true value are basically indistinguishable from one another. They're really, really close together. So when we talk about this transient, we typically talk about in the order of magnitude of a couple of time constants. This is a time constant of 1. And so that's where 1 is. And kind of by about 3 time constants, we're right there. Now, an interesting thing that we just, like while I've got this here, I just want you to kind of just observe a couple of obvious features. The obvious features are that if I change the gain of the first order system, obviously the effect of that is just to magnify or reduce the magnitude of that response. It's kind of a trivial, everybody should have seen that coming from miles away, right? What is not quite as obvious is that when I increase the frequency of the sinusoid that I'm forcing with, and so this is like what they call this a forcing function or a forcing sinusoid. Remember, the blue sinusoid is the input. I've kept the gain the same and I've increased the frequency. And what I observe is that the magnitude of the output becomes less. Now, if you're thinking about this in terms of our tank system, how you can explain this to yourself is that you can say, well, the tank, remember, has a certain size. And when the input changes faster, that doesn't mean it's actually larger in magnitude. So remember what we said. It's the amount, it's how much the flow rate is increasing that drives the rate at which the tank fills, right? And remember, the magnitude is staying the same. But when the frequency increases, it is high for a shorter amount of time. And when I have a short amount of time to fill up my tank, the tank will fill up less. Does that make sense? And so you can imagine that if I'm just bashing it back and forth really, really quickly, there's almost no time for the tank to start filling up, and then it's already like emptying again. Right? So it's important to understand this derivative idea that if there are dynamics in the system, basically every real system has this property that the faster I move the inputs back and forth, the smaller the actual magnitude of output movement becomes. So low sweeping changes across the road, right, makes you weave all the way across the road. But if you make the same changes to your steering wheel, but you just go really, really fast, you'll still, like, you'll judder around, but you won't be moving all the way from the left to the right of the road. Why? Because it takes time to move across the road. And so even if you're making the same changes to the steering wheel, if you're doing it quickly, you'll move less. And if you're doing it slowly, you'll move more. Now, the upshot of this is that, and we'll get to the way that we diagram this, but I want you to kind of have this idea that real systems typically have low frequency responses or low magnitudes of frequency responses at high frequencies. The other thing that I want you to notice is that if I decrease the time constant, that has a similar effect as decreasing the frequency. And that shouldn't be a surprise to you, because remember, the time constant is almost like the size of the tank in this case. And so a tank with a small time constant will respond quicker than a tank with a, so that's like a small tank versus a big tank. I'm doing the same changes in flow, but a small tank will fill up faster than a big tank, given the same flow, right? And so in most cases, you can see that when I decrease the time constant, the magnitude of the response is opening up. Cool, I have time. Right, so that's the first thing, and like I just want to stop here for a minute. Like, is everybody following what's happening here? Okay, so I've appealed to your intuition, and I've showed you the math of a single sinusoidal response. And at this time, you'll notice that I will use almost like basically having them as synonyms, sinusoidal responses, frequency responses. Those two concepts are basically the same to me. So when you say, what's the frequency response? A little bit later, when I say frequency response, I will mean the response at many different frequencies. But for now, we can kind of say the sinusoidal response or the frequency response at a particular frequency is this. And those will mean roughly the same thing. And so one test like this is not particularly useful. So if I just know the sinusoidal response of a particular system at a particular frequency, that doesn't really give me a lot of information about the system. But it turns out that if I have the sinusoidal response at many frequencies, I have something that is equivalent to the system's transfer function. I'm going to go to the math in a second, but I want you to just remember that Fourier series are the periodic, the way that you probably kind of encountered Fourier series were as the periodic version of Taylor series. So in other words, they are both approximation methods. And the basic idea is, I give you some weird function, and I tell you that it's got some crazy nonlinear description, and I am looking for a reasonable approximation which has all the beautiful properties of the polynomials. And you tell me, that's awesome, I can totally do that. I will approximate this by a polynomial using Taylor series expansion. Right, so that's the idea behind Taylor series, is that I have a function, some original function. Right, okay, so if you remember anything about the concept of Taylor approximation, that's what you should remember, right? Now, it turns out that there's another option where I could use what's called a Fourier series, and the Fourier series says I'm going to take that and I'm going to approximate it not by a polynomial, and these things are called basis functions. These in this case, it's t to the I. It's a family of functions. So there's t to the 0 is like a constant, and t to the 1 is a linear function, and t to the 2 is a quadratic, and so on. And we're using those kinds of things and adding those things together with coefficients to get this approximation. And the Taylor series specifically is one answer to the question of how do I know what to choose for A, for each one of the A's, right? And you can do the same game and say, let's do this thing. Let's call this h of t, And let's do that as some a's times sine of omega t plus b's times cos of omega t. And actually, a lot of you don't actually encounter it in this form, but I want you to remember that this idea of kind of having a sine and a cosine together, you can kind of get the same. You can get the same effect by taking an exponent of a complex number, right? And so you can kind of say, well, actually, I'm getting these coefficients of e to the omega t I plus, like whatever the real component is. But those map to the same kind of idea through Euler's identity. So don't quote me on the formulas that are on the screen now. Quote me on the formulas that are on the screen now, which I've checked. Okay? So that's the basic idea. I just want you to kind of picture in your mind the idea that, okay, I have a weird function, and I have these two roots. I can go a polynomial route and say I want to approximate this thing as a polynomial, and the Taylor series is one little subset, like one answer to the question of how do I choose the coefficients of the polynomial. Doesn't work for everything, as we've discussed before, but it works well for the analytic functions which we use normally in engineering. The Fourier series is a different approach where we're choosing these other basis functions, the exponents or the exponentials. By now, you should have a little bit of a tingling in the back of your mind saying, oh, wait, but that sounds like it would be very useful for the kinds of things that we do differential equations for, because that's the basis functions for the solutions of linear differential equations, right? So it may already be useful just to like pose the function in that form, which is why Fourier did it in the first place. So we've basically got this thing where we have this series. And you can see we are approximating this function as the sum of all of these exponents summed up. And remember that that's the basic idea, and then the actual implementation, because now I've got this question again of how do I choose those coefficients. When I did Taylor, I had this formula, right, with the factorials at the bottom and all of that kind of stuff. And like that was like the reason why Taylor was famous for his series is not because he came up with the idea of approximating stuff as polynomials, but because he came up with a formula, a foolproof way of finding the coefficients. And Fourier is famous for the same thing because he came up with this formula for the coefficients in this case. Now, if you look at that, you will have seen this in your books when you did Fourier series expansion. You did many Fourier series expansions. And if you kind of squint your eyes right, you'll notice that this thing here is this thing called the Fourier transform. And it doesn't take a great leap of the imagination to understand that those seem to be very, very similar. Right? So the one on the right is the Laplace transform, and the one on the left is the Fourier transform. And that's the coefficient formula for the Fourier series. And you can see they have this very strong family resemblance. They're all integral transforms. They all take the original function and they integrate. Now, in the case of the Fourier expansion, we are integrating between the bounds of the period of a repeating sequence. Now, I'm going to show you, I cannot tell you how proud I am of this notebook. Because when I did this and it worked, my mind was completely blown. So I'm going to show you how this actually works. Firstly, it is true that SymPy can literally just take the definitions that I took here from a book. And you can code that into SymPy in a very, very straightforward way, right? So that's the formula for the sum there at the bottom. And you can see I've tried to keep really close to the transcription model of the of math to code. So I've just taken the sum of these coefficients times that for all of these, right? And the same way for the Cn, I'm just doing integrate this thing times this from between these bounds. I've taken exactly the textbook definition. And then I've taken a function which is just a diagonal line. Now this is actually, when you think about the true, if you were doing this in math, I would make a big deal of it that actually what that approximation is for is that's the equation like t, right? But remember, we've got this period of repeating, and so actually the thing that we're going to be approximating with our Fourier series is this repeating unit that repeats forever in both directions, like a sawtooth, right? So that's actually the function that the Fourier series will approximate. It'll, if we just zoom in on that little period, like it won't bother us. And this is why you can use the Fourier series for pretty much any function. But just be aware that that's going to happen in the plots that we'll see now. So if you keep going on this, let me just see. I have to run it. So let's go. Okay, so and there you go. Like this by itself is super amazing, right? That you can like write the stuff into SymPy directly from the textbook. And you can put that function in there, and you get out the correct answer. And that's legit the correct answer, because if we plot it, that's what it looks like. Okay, no, this is not the amazing part. This is like not even remotely the amazing part. This is just like, yes, they didn't lie to you, like when they told you about Fourier series, okay? Unfortunately, it is true that that's really easy to understand, but it's super slow. And so I'm going to use more terms, and there's like a built-in function that does Fourier series expansion in this package called MP-Math that used to be part of SymPy, but is now kind of branched out into its own package. And I'm going to do something very interesting now, which kind of explains why these things are actually useful. I am going to take a completely different approach to finding out what the step response of a function is. I'm going to take that step, right? And what I'm trying to do here, let me just explain, is the stuff that we've been doing all the time. I'm going to take a step, I'm going to put it into a transfer function, and I'm going to try and figure out what the response looks like. The sum of lots of sinusoids, calculating the sinusoidal response of the transfer function using the formula in the book. And then I'm going to add all those sinusoidal responses together. And if everything is right, I should get exactly the same response by adding up those sinusoidal responses. Now check this out. So I'm gonna go through this quickly because I just want you to see what these look like. So that's basically the input signal decomposed into those sinusoids, right? So I've got my step. In order to make this an odd function like the sinusoids, like the Fourier series likes, I've kind of shifted it down a bit. But the step is, in other words, going from there up to there. Okay? And you can see these blue curves are all the composite sinusoids from the Fourier series expansion. And this orange curve is all of those things added together. So I've got this one low frequency one, and then I've got like a slightly higher frequency one and a slightly higher frequency one. I've got 20 different sinusoids there, and they all add together. Now, I'm going to take each of these functions, and you'll remember that what we said was that the response, this sinusoidal response, the sinusoidal response that we were talking about earlier, notice that it is different in magnitude, but it is also out of phase with the input sinusoid. And we can look in the book and get the formula that says how much does the phase change and how much does the amplitude change for a first or for the kind of function that we're talking about. I've used those formulas directly. Now that is the analytic response of the little second order system that I'm simulating. And I'm going to build sinusoids. And I just want to show you the key part. I'm going to build new sinusoids that are changed in magnitude and shifted from those original sinusoids. And there's the reveal, right? Here are the original blue. The blue signals are the original sinusoids. The green ones are the sinusoids that have been shifted and scaled by the frequency response formula. And when I add all of those green lines together, miraculously, I get the full step response. Now, this is the motivation that tells you when I have a full frequency response, when I have all the component sinusoids, or when I know how the system behaves on component sinusoids, that's the same as knowing the full transfer function. Because if I know how it shifts pure sinusoids, I know how it shifts any signal that can be represented as a sum of sinusoids, which Fourier told us is any signal. We were talking about this idea of understanding the way that systems respond to any kind of signal by understanding the way that they respond to sinusoidal signals. And if you stuck around till the final part, you will have seen me showing you this Fourier series notebook where I showed you that you could take any signal and decompose it into its component sinusoids. And this idea is a very huge idea, and it motivates kind of the Fourier series. I don't know if any of you watched the Fourier series video that I posted on Slack. Shout out to 3 Blue 1 Brown. That's a really great channel. So if you at all interested in math, like just binge that channel. It's totally worth it. So the reveal, if you remember, was that we could that we ended up with this kind of combined signal. And I just want to kind of, because I think that it wasn't 100% clear to everybody. The idea that we were trying to do was we had a signal which was a step signal. And we were doing our standard step response question, right? We were doing the standard simulation question. We had a system, we had a step input, and we were asking the question, what will happen to that system if I apply that step input into that system? But we were solving it in a completely different way, because what we were doing is we were decomposing that step into its component sinusoids. In other words, we were writing that step as a Fourier series. Then we were using the idea that we started that lecture off with, that if I took a pure sinusoid into a system, I would get a pure sinusoid out, but it would be changed in magnitude and in phase. In other words, we can see here that's the original sinusoid, right? And the response sinusoid is shifted, that's called the phase, and it is multiplied by some kind of magnitude. And so these sinusoids, they take this this form of sine of omega t plus phi. And so we call phi the phase lag. And just to be incredibly clear, phi is not the actual time amount that the shift. So when you look at that curve, it's a common error for people to imagine that this is phi. But remember, phi has units of radians, right? And this time axis is actually a time axis, so it has units of time. And so if you want to write this into a form where you actually look at the shift amount, you have to kind of take that in and write it as a coefficient of time. That's in the formulas or in the book. I'm not going to go over that again, but just be aware, when I say phase shift, what I'm talking about is an angle in radians, not a shift in time. There are some calculations that relates phi to the actual amount of time. It's not a huge calculation. It's just like you have to divide phi by omega to get into to get the shift angle, right? So that was what we ended up with. And if you were looking at that result, what you should be looking at here is the blue curves are the components of the step, the Fourier series just plotted of the step, and the green curves are the Fourier series of the step response that we obtained by applying this multiply and shift logic to every one of the components in the input step. And what I also want you to understand is that this is a completely different way. We've now covered 3 fundamentally different ways of getting a step response of a system, right? The first one was to solve the differential equations analytically, right? And that involved symbolic manipulation, like use an integrating factor or any of those ways that you use to solve the differential equation. We showed that the Laplace transform effectively was a different way to do the same calculation. Like we took a side step, but that's still an analytic calculation. The second way is to solve the differential equations approximately by using numeric integration. That's what we're showing when we show open modalica, or when we use the control library to get a step response. They're all using numeric integration. This is a whole different way. In other words, fundamentally, we are doing completely different set of calculations. This is neither an analytic nor a numeric solution, right? This is an approximate solution that is obtained through the Fourier series. Now, I just want to take you back to this second order response notebook, and hopefully by now some of these things will make a little bit more sense than the first time you saw it. You can see I've got a second order system here where I've got sliders for the various parameters. Importantly, you can see here is a pole of the system, and by now you're like, oh yes, I know exactly what poles are, right? And remember that those poles move, and their nature changes because of the way that, because of zeta. And so we can now very clearly see when we start playing with this that, well, at that moment when zeta is equal to 1, we get repeated real poles. When zeta is larger than 1, we get these 2 distinct real poles. And then when zeta is less than 1, they suddenly become complex. Okay, and so that's the first thing I want you to see, is that those complex poles kind of emerge easily over here. And remember the way that we interpreted this, I showed you an animation where I showed you, and you can see on the right-hand side here, you can see the real and imaginary components of e to the st. And this dot that I'm moving around with my mouse here is s. And if you remember that we talked about the Laplace domain as being the space of this, all of the exponential family. So every point on the S-plane represents a particular kind of exponential response. And so you can say, okay, so where do responses live that look like nice non-oscillatory responses? Well, they all live here on the real line, right? And you can see there we have the imaginary part, which is, remember, the brown line is just 0. And the real part is just this beautiful, nice, stable exponential. When we move to the right-hand side of the plane, we can see that's where unstable responses live. So all of the responses there have a real part or a positive real part, and that positive real part means that those functions are all unbounded. They go to infinity. We call those unstable responses or unbounded responses. And we can see that oscillation happens when S has an imaginary part, right? So we can see that those kinds of functions live away from the real axis. If we want oscillation, in other words, we need to have an imaginary part in the exponential. But something very special happens when we hit the imaginary line. At that point, e to the st becomes a pure sinusoidal response, right? And that's the first thing we just notice. We notice, oh, okay. And to a certain extent, you'll hear me say this a couple of times. If S is a space where all of the exponentials live, right? The stable responses live on the left-hand plane. The unstable responses live on the right-hand plane. Non-oscillatory responses live on the real line, and the pure sinusoids live on the imaginary line, right? They have a space. They have a place where they live. Now, the last thing I want to show you just that links this is if we now take a transfer function, and I'm going to do something interesting here. I'm going to do a 3D version of a transfer function. So I'm just going to take take G, I'm going to define G of S. I'm going to specifically define a second order transfer function that has an oscillatory response, aka complex roots, aka less than 1 zeta. So I'm just going to take S squared plus S plus 1. That's an easy one to kind of imagine. Now I've got to actually, so that I'm just going to define that, which in GeoGebra means like I'm using a colon equals. And I'm not going to plot that, but what I am going to do is I'm going to plot G of X plus Y times I. And I'm actually going to plot the magnitude of that. There you go. Okay, so what we're seeing here is the magnitude of the transfer function G of S for this second order function. And hopefully if you look at this, you will realize that this is why I feel that the word pole is a really well chosen word. Because you can see that at the location of the poles, if you picture this surface being like one of those tents, right? The location of the poles like actually pushes up the tent at those locations. When we do our standard transform, substitute S is equal to I omega in the transfer function. Now what does that mean? If omega is a real number, I omega is the imaginary line. And so that's a very satisfying result, right? Because we know that I omega, in other words, that imaginary line, that's where the sinusoids live. And if we're thinking about a frequency response, then the response of the function at that point will tell us something about how much that function has of that sinusoidal component. Remember when we spoke about poles initially, I said at those places where it's infinite, you can think about the Laplace transform being like a resemblance function, right? And it's saying like how much does this function kind of resemble those functions, or how much of this component does it have in? When we were allowed to traverse the entire complex plane, we could find points that were maximally matched, like infinitely perfectly matched. And we could say, when we look back, we could say, oh, those exponentials at these infinite points where the Laplace transform is large, those are the components that we can just add together to get the function that we Laplace transformed in the first place. Well, the poles are the roots of the characteristic equation. The roots of the characteristic equation tells you which of the exponentials to add together. And those are the biggest points on the Laplace transform. So the Laplace transform is like a lens for finding like which of these functions are like this. But it's kind of hard to plot this. And so what we'll end up doing instead, now what I've done there is I've added the real, or that's the complex line, but it's a plane that's like just cutting through the complex line. And you can see, if we look at that, that in other words is the magnitude of the frequency response of this system. So that intersection of this full surface with that line is the frequency response. Check this out, right? Here's how I calculate the frequency response in for that second order system in Python, right? I have S, or I choose a lot of different omegas. I multiply that by 1j, which is the complex number in Python, and I literally then just calculate. In that one line, I calculate the frequency response because I'm just plugging in I omega into that transfer function.